Suppose we have some function x squared. Let's pick an input and then move it a little. As you can see, input moved by 0.5 and output moved by 3.25. And we can represent this change in the input as delta x, which is new value minus previous one, so it's 0.5. And the same for the change in the output, where we just subtract the f at 3 at previous value from the f at new value 3.5. So in general, this notch input can be represented as x plus delta x and its output as f at x plus delta x. And therefore, the change in the output in general form is f at x plus delta x, which is new current value, minus f at x, which is previous value. So let's plot every part. It looks like that. And now let's make the notch smaller. And as you can see, both changes had for nothing. So the delta x is approaching 0, and same for delta y. And it means that neither change on its own says how the function behaves here, but we can compare them. So, as you can see, the same notch at x at two different places produces different response at y. And we can put one change over the other, and this new value is a value which tells us the number of units of output per unit of input. And in general form, this value can be written as following, where at the top we have the change in output and at the bottom we have the change in input. And we can use this one number to describe how hard the output answers. Now let's shrink the notch, and as you can see, the value settles to some value. In our example, this value is closing a number 6 as the notch is made smaller. And as we said, the response depends on where we are on the function. And moving on the right, we can see that for this function, the output responds more. And the derivative answers how much does the output respond to the small change in the input at this point. Let's try to understand the geometrical meaning. So when we do the notch, we have 2 points, current and new one. And that right here is the slope of a line, of this second line, and the slope says how much a line claims for each step across. So in this example, as you can see, when we do a step by 2 at x, the output y increased by 8 units. So its slope is equal to 4, because when we move on x by 1, the new value at y is going to be equal to 5, increased by 4. But that's the slope between 2 points, not the slope at some certain point. Therefore, we can bring the second point closer to the first one, and this slope, this line becomes a tangent line. And this value now is the slope of the tangent, so it's the slope of the curve itself at this point x. But each notch gives a line and a slope, like a notch by 2 gives a slope 4, a notch by 1 gives a slope 3, and so on. But we can see that smaller notches curved the slope towards 2 at this point. But we cannot make the notch equal to 0. 0 is just the smallest notch of all, and if we put it into the equation, the result is going to be undefined. So the notch never becomes 0, but we can say that this notch is approaching 0, and we use a limit to do that. So this equation, limit of this radius is equal to 2, means that this 2 is the value heads for as the notch shrinks towards 0. And instead of substituting every point at the equation, let's just write it in general form using x variable. So it looks like that, and that's our derivative. So the derivative is a slope at a point, or a rate of a change at a point. Let's run it once on x squared. And as you can see, the result is 2x plus delta x. And when delta x is approaching 0, when the notch is approaching 0, the output is 2x. So that's our derivative. Derivative of x squared is 2x. And this answer is not a one number, but it's a formula. And now we can fit any point to that formula to get the slope at this point. And actually we can extract the angle between the slope and the axis. So as I say, the slope is delta y over delta x, but we know that the tangent of the angle theta is opposite, which is delta y, over adjacent, which is delta x. So we can say that this tangent of theta is our radio. Therefore, for some derivative at x is equal to 0.5 and the derivative is equal to 1, we can see that the tangent is equal to 1 as well, meaning that the theta is arctangent of 1, which is 45 degrees. And we can do that for any point. And there is some special case when the angle is equal to 0, meaning that the derivative is equal to 0. And this flat tangent marks a place where the curve stops rising or falling. We'll move back to that later. So now let's take a closer look at some part of the plot. And let's zoom in far enough so the curve looks like that line. So the curve actually has not become straight. We are just looking at a piece of plot small enough for the band not to be shown. And it means that near a point, the function is a straight line. And therefore we can approximately calculate the next value after the notch, after the small enough notch, having the function and its derivative. To do that, we use this formula. For example, at x is equal to 1, with different notches, we have following approximation and two values. And as you can see, with smaller notch, we can approximate the function with the lower error. And if you're worried about those limits, it's better to not do that, because I've just shown you all those limits to understand the core idea, but nobody runs that limit twice, just once to understand, and after that they are just looked up at the table. So here you can see the table of some common functions, which are derived in the same way I showed you before. And for example, the derivative of x squared is a sort of our table, where the n is equal to 2, so it's just 2 times x in the power of 2 minus 1. So it's 2x. When you have x in power of 3, it's just gonna be 3 times x in power of 3 minus 1, so 3 times x squared. And there are 4 main rules for combining all those derivatives. First one is that the derivative of constant times function is just constant times the derivative of function. Second one is that the derivative of sum of two functions is the sum of two derivatives. And the most important one, the derivative of product, is the derivative of first function times the second function plus the first function times the derivative of second function. And the last one can be derived from the derivative of product. So you can see some small examples, just pause the video and verify them with the table. Now let's move back to the tangent line. And let's slide the tangent along the curve. So as you can see, it's going down and the derivative is negative. After that, the derivative is equal to 0 and the tangent is flat. And after, it's going up and the derivative is positive. So the sign of the slope is the direction of travel. And as we say, the derivative is function 2. And at the top, you can see the function x squared and the bottom is the derivative. And the left part of the derivative plot shows that the function is decreasing in that interval. And the positive part tells us that the function is increasing at that interval. And where it's equal to 0 tells us that the function has 0 slope, so it's equal to 0 as well at this point. And it's important because the point where the slope is 0, that's the point where the curve changes direction. So here you can see some local maximum point, because before this point we had rise, and after that the function was falling. Therefore it means that at x equal to minus 1, we have the function has local maximum. And the same for the second point, at x is equal to 1, we have the decrease on the left and increase on the right, meaning that the function has the local minimum at that point. So to summarize, there are 3 cases, and that's all. First one, the function is increasing when the derivative is positive. Second one is the function is decreasing when the derivative is negative. And the last one, when the derivative is equal to 0, the function is locally flat. But now what happens if we have a function with a lot of inputs, like multivariable function? We know that 2 inputs create some surface, for example like that. Here I have a function where the x and y are inputs, and the output value of function, that coordinate is the height. And now we want to understand how the height responds to each input. So to do that, we just need to pick some value of y and fix it, so we hold the y fixed and move along x. Therefore, the plot looks like that, where for different x values we have different z values, like function outputs, and we can calculate the derivative of f relative to the x when the y is fixed. It looks like that, and therefore use this derivative to calculate the slope of that equation. And we can do the same for y just by fixing the x and calculate the derivative of function relative to y. And to do that, in our example, we just differentiate one input holding the rest fixed, meaning that for derivative of function relative to the x, we consider as the y as constant, and therefore we have derivative of x squared, which is 2x, plus derivative of some big constant 3y squared. And we know that the derivative of constant, and we know that the derivative of constant is 0, so it's 2x plus 0. And the same for y, considering the x as a constant. Therefore, at point 1 and 1, we have the derivatives like that, and the first one derivative shows us the response of the function to the change in x, and the second one shows the response of function in the change y at this point. But that's what happens when we do changes independently at each axis. But what if we have the change, a step, that follows neither axis? For example, let's create the .x vector, like the change vector, which consists of two components. Delta x, the change at x, and the delta y, the change at y. And we change both inputs at once. So let's see how f value is changed. To do that, we just take the step into two stages. First one, we just calculate the height, like the f value, gained by the x change. So it's just derivative of function relative to x. By the way, this derivative is called partial derivative of f with respect to x, and the same for y. So we just multiply each partial derivative with corresponding changes, and the result is the height gained by that movement. Therefore, we can see that from the x move we gained 0.4 height, and from the y move we gained 0.6 height, and together it's 1. Therefore, we can represent the change of the function value as following: just sum of partial derivatives times their changes. And we can rewrite this sum as a dot product of two vectors, where the first vector consists of two partial derivatives and is called the gradient, and the second vector is our change vector from delta x and delta y. And that's how we can rewrite the sum as the product of gradient times delta x vector. But actually, we can represent this delta x step vector as some constant h, which is like step size, times some unit vector. So we just decompose this vector in two components, the trend and the direction, where the direction has the unit length. Therefore, the change of function looks like that, and we can divide both sizes by the step size, h, and doing that, we now calculate the change in f per unit distance in the direction of u. We obtain something called directional derivative. So this new formula is the derivative of function f in the direction of unit vector u, and this derivative shows the change in f when we do the unit step along vector u. So if this derivative is equal to 5, for example, it means that when we are moving locally along the direction of vector u, the output of function, the height, is going to be increased approximately on 5 units per each unit. By the way, the partial derivatives with respect of x and y are actually directional derivatives along a coordinate axis. Well, and now we can see that every direction has its own rate of change, and which one is the largest. So suppose we have some gradient vector which is equal to 2 and 6, so there are partial derivatives to x6. So we move by 2 units at x and 6 by y. And this vector looks like that blue line. And let me recall you that this directional derivative is equal to the dot product of the gradient and vector u. And from the geometrical meaning of dot product, we know that it's the same as the line of the gradient vector times the line of the u vector, which is in our case equal to 1 because it's unit vector, and times cosine theta, which is angle between the gradient and u vector. So when this u vector has the same direction as the gradient vector, it means that the angle is equal to 0, therefore the cosine is equal to 1, and this derivative is the largest it can be, because the gradient is in full length. When it's perpendicular, the cosine is equal to 0, and it means we have no change at all, and the derivative is equal to 0. And when it's equal to 180, as this red arrow, cosine is equal to -1, meaning that the derivative is minus gradient length, so that's the most negative value. Therefore, we can conclude that the largest change of this function happens when we are moving, when we are doing the step, along the gradient vector direction. So let's look at this surface from above. And as you can see, we have a lot of points with the same height. So each line is just a contour where the height is the same. And when we do steps along a contour, nothing's going to be changed because the height is the same, right? And it means that the gradient is perpendicular to our direction and the derivative is equal to 0. Therefore, for this surface, if you want to move in the direction of the most change, we need to move in the direction of gradient. By the way, for example, if you have some two contours with the head 1 and 2, you can see that there are places where the contour is closer to the previous one. And it means that at this point we have a steeper surface because like the distance is smaller. So suppose we have some neural network model. And this model is actually a function of some weights, and these weights are just inputs to that function, and this function produces some prediction y hat. And we use this prediction to calculate the loss function. This loss function is also a function of the weights, where the output is the difference of ground truth and prediction value. So until now, I was showing you the function, which was just any surface at all. But a loss is a surface we want at its lowest point, meaning that the error of the model is the lowest. So for all combinations of the weights, we calculated the losses, and now as the current weights at top, we want to move toward the lowest loss value. So let's do it for one input value. Suppose we have some w is equal to 4, and the derivative at this point is equal to 6. So as you can see, the slope at this point and the derivative is positive, meaning that when we increase in the w, it rises the loss. So we need to move in the opposite direction. We need to go left. And when the w is equal to 0, we can see that the loss is equal to -2, so it's negative, meaning that when we are rising w, it lowers the loss. So we just keep on moving in that direction and go to right. And that's the whole idea. To do one step downhill, we just take the current state, like the point where we are, and subtract some coefficient eta, which is like the learning rate called in the machine learning, and which is just the step size, times the slope of the loss at this point. And it's pretty logical, because as I said, when the derivative of this loss function at this point w is positive, we need to move to the left. And that's why we subtract from the current point w some small change and moving to the left. And when this derivative is negative, we are moving to the right. So that's why we have like minus and negative derivative, so it's plus. So we just add to the current point some small change. For example, w is equal to 4 and the derivative is 6, and some eta is equal to 0.2. We do the step, and the new value is 2.8. So we just made a one step downhill, and that's the whole idea. And now we just repeat that, and steps just shrink by themselves because the slope is smaller, so we are doing smaller steps, and as a result, no step is just ever taken uphill. But in reality, a model has more than one number of inputs. But the good news is that nothing changes. We just have one slope for each parameter, and instead of derivative of one function, we use the gradient, which is actually the analog of derivative for multivariable function. And we know that the gradient shows us the steepest increase of the loss, like of the function, in this case the loss function. Therefore, we just need to move in the opposite direction, which is steepest decrease. And we already have that. We have w minus gradient L. So that's what we needed. So for our surface, let's see different contours with the same height. And suppose we are in the point 2.4 and 1.6, and the gradient is 4.8 and 9.6, with the step size equal to 0.1. So that's the first step we do, just by moving in the opposite direction of the gradient. And the loss is decreased from 13 to 5. Then we do it again. And as you can see, we are approaching the minimum. And the loss follows at every step. And that's actually what a gradient is doing in neural networks and optimization. By the way, we need to be careful about the step size, which is learning rate, because when it's too small, we need to do a lot of steps to approach the minimum. And when it's too large, we just can accidentally skip the minimum. So to summarize, training a model is this loop where we do prediction, measure the loss, take the gradient of the loss function, and step against this gradient, updating the input parameters to the model, and repeat all the steps. Now we can move forward to the chain rule. And we know that a model is a stack of stages, so its loss is a function of a function. Like in this example, y is a function of u, which is also a function of x, meaning that when we change the x, like x is equal to 1, it firstly changes the u, which is equal to 4 in that case, and only after that, this change the t value changes the y value, so it's equal to 16. Therefore, the chain rule tells us that the derivative of y function with respect to x is just the two local rates multiplied. So it's just derivative of y function with respect to its input u times the derivative of u function with respect to its input x. In our case, it looks like that. And we can have a chain of any length. And the idea is the same, we just have one local rate per stage and just multiply all of them together, moving from the left to the right. So the derivative of y with respect to v times the derivative of v with respect to u times the derivative of u with respect to x, and so on. So let's do this forward step just by substituting 2 at x. So a is going to be equal to 6, b to 7, and y to 49. And now we do backward pass, just finding these derivatives and multiplying them. So the derivative of y with respect to b is 2b, and the b is equal to 7. And same for derivative of b with respect to a, so it's equal to 1, it's just equal to 1. And derivative of a with respect to x is just equal to 3. And now we can stack them together, moving from the left to the right. But what if we have one input, t, which has an impact on two variables, x and y, meaning that if we move this variable t a little, and both of them change z value. And it's pretty obvious because the effect of t on z arrives twice, so we just multiply it along each pass, and then add across passes. So the derivative of z with respect to t is just the derivative of z with respect to x times the derivative of x with respect to t, to its input t, right? Plus the derivative of z with respect to its second input y times the derivative of y with respect to its input t. So that's what happens when we have a function of two inputs, x and y, but x and y are controlled by one initial input t. So as I said, a model is a long composition of functions, whereas a double is a vector of adjustable parameters, and f1, f2, f3, and so on are stages where each fit in the next. And y hat is a prediction of the model, and the loss function is one more function which tells how wrong the model was. But how does the changing of w vector change the loss function? And this is where we use chain rule. So each stage says how sensitive its output is to input, and this change, like the derivative, which is the change of the loss function with respect to w, meaning with the change of w, is just the derivative of loss function with respect to its input, which is f3 function, times the derivative of f3 function with respect to its input, f2, times the derivative of f2 with respect to f1, and the derivative of f1 with respect to w. And it means that if we change the parameter w, it doesn't affect on the loss function L directly, but this change goes through the whole chain, affecting every function. And that's why we do this chain of derivatives just to take into account the sensitivity of each step. So we just combining the change of W and F1, then we take into account the change of F1 by this change of W to the change to the F2, then change of F2 caused by the change of F1 to the F3, and then the effect of change of F3 caused by change of F2 to the loss function. So, three core ideas of that video. First one is derivative of f at x. Tell us how fast the output changes when x changes. So it's just local slope. Second one, the gradient of the function is a derivative when we have a lot of inputs, and it's a vector which consists of all the partial derivatives, and it contains the local sensitivity with respect to every input independently. And considering it as a vector, it shows the direction of the fastest growth. And the last one, chain rule. That happens when one function is the input into another function, and then all the local rates are multiplied along that chain.